you. And then they're like, what is it? Is it rolling? How long am I supposed to help you?
All right, my friends. First I have a trick.
Yo.
Has anybody seen me do the string thing before? I feel like I've done it at least a couple of times. I learned this in 3rd grade, and every once in a while I just do it again.
Whoa.
Thank you, thank you. Got a couple others.
I'll save them. I don't want to blow it all today.
All right, homework assignment created finally. You're welcome. I know. Yeah, it's a good one. It's not too bad. It's honestly not too bad. I want to talk a little bit more about the Gauss-Legendre quadrature. Not too much. I want to talk about what we do if we have an improper integral. So, for example, something that has infinity in the limit. How do we handle that? You won't be doing that on your homework, but you will be doing that on the final. So the final's probably going to have a little bit of everything kind of in it, just a little bit of like, let's go back and just pull it all together kind of stuffs. And we'll go through this assignment that I did post in World Class. It's in the assignments. We'll talk more about that in a minute. Let's get some stuff done here. So, remember what we were doing?
That is somewhat rhetorical question. We have this dude here. We're trying to approximate it in the simplest, lowest effort way possible. And so we saw that we could, at least for a couple of cases, find some weights and some integration points. The weights w sub I and the integration points x sub I that gave us a pretty good approximation. Now, I'm putting equals here, but there is some error on that. If I want to write equals, I better put that over there. And I think that'll be the kind of thing we maybe investigate in the final just a little bit. Right now, I just kind of want to play with the beauty and power of this method. So we solved some systems. Labina solved some system like literally Good Will Hunting style when we had n equals 2. So that's the number of nodes. Let's see. So when we had n equals 1, this right-hand side was 2f of 0. So our w, our weight was 2. Weight 1 is 2. And our x integration point was 0. And then we did some work, and this is part of your extra credit, this extra credit assignment. I don't know when I said it was due. What did I say?
Next Friday.
Next Friday. Wow, that's a long time. Cool. No problem. I also sent out a tip in the email for a really just concise way to break it open. Did I do that?
Yes.
Okay, cool. And what we saw last time was that if we want to write this thing as a W1 f of x1 plus W2 f of x2, and have that be exact on a cubic polynomial, right? Remember, this is exact on a cubic, this is exact on a linear. The next one would be exact on a quintic, a 5th degree polynomial. So these things are always going to be exact on odd degree polys as we move up. And n is the number of nodes. So this one here we saw was just 1 times f at negative 1 over root 3 plus f at positive 1 over root 3. Just kind of incredible. Just freaking amazing. So anytime somebody asks you to do a definite integral of a cubic on a finite interval, right? So it's got to be definite and a finite interval. You can literally just crank that out and impress them, just blow their mind. Because most people, honestly, a lot of people don't know this. So your science teachers, this is not super well known unless you're really deep into numerical methods.
I was telling some colleagues about it, and they seemed like they knew, but I kind of feel like they were just, I don't know that they knew. That's all good. So then we could do n equals 3, n equals 4, blah, blah, blah. But as you saw, this system was kind of intense. This was a nonlinear system, so to find these weights and these nodes, we had to solve a system of equations, and it was 4 nonlinear equations. And that's what makes it so brutal. Linear equations would have been cake. That's just a matrix. We were solving that. But we had 4 nonlinear equations to solve in 4 unknowns. The next one's going to be 6 nonlinear equations in 6 unknowns, 8 nonlinear equations in 8 unknowns. Yeah, exactly. It's like eyebrows going up, right? Because this is brutal and painful and maybe not even tractable, not something we can solve in a finite amount of time. So how can we get the rest of these nodes? Well, the cool thing that the Legendre part of this, remember this is Gauss-Legendre quadrature. The Legendre part kicks in because these nodes, these integration points, and these weights come from a family of polynomials. Remember the Chebyshev polynomials when we did interpolation? The zeros of those Chebyshev polynomials gave us the perfect spots to interpolate on. They, instead of like trying to find the optimal curve up here, we tried to find the optimal place to make that curve, to sample for that curve. So these, the integration points, and weights can be found from the Legendre polynomials. And this is a family of polynomials. I'm going to see how much of this I can remember. I prepared, I reviewed this. It's just this formula is a little funky. And so we start off and build these inductively. The first one is just 1. Doesn't even have a 0. Doesn't really come into play. The first one is x. So we initialize this process with these 2 polynomials. We're going to say the first one's 1, next one's x. How do I move up the chain? And so now I get a recursive relationship that says the n plus first poly is equal to, don't write this down yet because I'm going to try it and then I'm going to see if I wrote it right. Pn of x minus, well, I don't remember anymore. It's those numbers out front that I don't quite remember. Not bad, not bad. Did pretty good. There's an n plus 1, and then this is p n minus 1. So notice we've got this recursion that feeds from the previous 2 polynomials to get the next one. It's like a Fibonacci sequence, where the next number is the sum of the previous 2, but you know, a lot more complicated and interesting. So we can keep cranking these up, and we're going to find the next couple together just to do it together. But let me give you the full lowdown on this before we do that. So the zeros of p sub n of x are precisely the integration points for n-point Gauss-Legendre quadrature. So if we can find these polynomials and then solve them, and we know how to solve we know how to find roots, right? We could even write a numerical routine to find these roots if we wanted. That was one of the first things we did in here. Literally the first thing we did in here. So
And the weights, of course, put corresponding weights. Corresponding weights are W sub I equals, now I gotta look this guy up. I didn't spend enough time trying to remember this formula, but that'd be a weird thing to spend time on. Check that out. This X sub I equals an integration point. One of the integration points I got from down here. So i.e., let's be even more precise, P sub n of X sub I is 0. But this is its derivative in the bottom. And looking at this formula, we can probably assume that these derivatives do not equal 0 at those points. Because like Gauss isn't going to roll with that. Legendre, they're not going to roll with that shit. Like this formula works, right? This is legit. This is well defined, and we can use it. So let's actually do P2 and then maybe P3 together. So could you do me a favor? So using this recursion, just to get your brain wrapped around it, could you please find P2 of X? And then if you get, super energized, find the zeros. They might look a little familiar. We kind of know what they should be already. What is n here, just so we're on the same page? What is the n here? 1. So be careful. If you put n equals 2, you're actually finding P3, which is cool, but you'll still need P2 to get it. So be real careful here. We want to let n equal 1. This was n equals 0 here. Oh shoot, shit, sorry folks, I left a variable out, I'm so sorry. There is an X in here, otherwise it's not going to. That's not a multiplication symbol, and I read it that way even though I was thinking to tell you, don't read it that way. So sincere apologies. That is 2n plus 1 over n plus 1 times the variable x times this previous polynomial. I'm so sorry. I'll put this up here just to lend some clarity. That is the recursion we want to compute. Once you get that, there's, it falls pretty naturally and easily. Are we cool on that? Awesome. Has anybody found the zeros? What'd you get, Christian?
plus or minus like 1 over root 3.
Yeah, beautiful. Does that make sense to everyone how to see that? Yeah, cool. We got this equation, which is really just this equation, which is this equation, and from there we get the nodes that we actually already knew. Does that sound good? Oh, cool. All right, that was good. That helped. That was a good sound. Not a sound of dismay, a sound of enlightenment. Fantastic. Let's go ahead and find the corresponding weights and just prove to ourselves that those weights are both 1. So let's use this formula here to see what the corresponding weights will be. And so in other words, this should probably say x of I because there's no variables in there. I think I didn't copy that I down, but that's got to be the case. I haven't done this yet myself, so I'm a little stoked to do it. So you will need P2 prime. Which is pretty nice. Yeah, not bad. Oh, it's squared, thank God. I was getting really scared for a second there. Squared. Do we get one? Yeah, okay, good. It looks a little dicey at this point, so I'm gonna have to keep cranking. Oh, I see. Yeah. And then that's just like 9/3. And then that's 3, yeah, cool. And we could probably convince ourselves that it doesn't really matter if I put plus or minus 1 in there because all the x's are squared. Or, yeah, everything ends up squared, so the sign gets kind of washed away. So we're gonna get those weights for both. Sound reasonable? Cool. I'm almost thinking it sounds silly to go ahead and do P3. I mean, if you understand this, you can do it. Maybe you'll do it sometime in the future. A month from now or so, something like that. A little less than a month from now. Is there any questions on this at all? So this is a great way to actually find these integration points and weights. And this is in fact what the NumPy routine that's in the code that I gave you does. It has these polynomials, it generates these polynomials, and it can solve for the roots numerically. And then once it has the roots, it does a numerical derivative, which we can do as well. So all this stuff can be turned into routines in a computer that we understand. I want to tell you one thing really cool about these Legendre polynomials. So the Legendre polynomials are orthogonal. What does that mean? What do I mean? Perpendicular, yes. How can a function be perpendicular to another function? What do we think that might mean? Any ideas? It sounds weird. Seems like it could mean they met perpendicularly. That would be one interpretation. But that is not the right interpretation. So I want to tell you something a little bit mind-blowing. It's an amazing math story. Every function that you ever encounter, and these are going to be functions on -1 to 1, not shockingly, because that's where this process takes place. That's what the the weights and the nodes are for. But every function, f of x, is actually a vector. So you're used to thinking of vectors as things like this, 3, 2, minus 1. And then you think there's 3 this way, 2 that way, and then down 1, right? So you can graph that by saying 1, 2, 3, 1, 2, and then you go down 1. So you might think of it as like a little 3D vector pointing below the floor down there. We can picture it that way. But there's another way to think of functions beyond this graph that seems more like this. So if I take a vector like this, I could think of it in a very different way. I'm going to kind of come in the back way, and then we're going to come in the front way, and they're going to meet. I could think of this as the slot, the vector slot, or the coordinate, you know, the coordinate position in the vector. And so this would be the first slot, this would be the second slot, and the third slot. And there's only 3 slots for a 3D vector. In the first slot, I've got a 3. In the second slot, I've got a 2. And in the third slot, I've got a minus 1. Now it's starting to look like a function, actually, right? It's starting to look a little like a function. It looks like a function that just has to be defined in this way. I spit out a 3 when x equals 1. I spit out a 2 when x equals 2. And I spit out a minus 1 when x equals 3. So I can turn this vector into a function. Likewise, I can take a function and see it as a vector with a lot more components. In fact, infinitely many components. So I can think of this vector, let's say I had x squared. Let's say I had good old x squared. F of x is x squared. So for me, this is a vector with infinitely many slots and a continuous output. So I could say, what's in the slot 1? Well, in slot 1 is 1 squared. It's 1. What's in slot 2? There's a 4. And what's in slot 0, 0, and then I can keep filling these all in. And you get this thing called a graph.
What? Or, sorry, I was being sarcastic.
What?
Something called a graph.
Okay. You can see my confusion.
Yeah, I can
Okay.
see you being really confused.
But you're not.
I'm not confused.
Not
about graph
remotely.
is, no.
You're so on this, you're being a smart ass about it.
Yeah.
That's good. I like that. That's what we need. This world, I want to encourage you to be a rascal as much as possible. I've decided I am fucking channeling Coyote, you know, the Native American coyote, the trickster. Like, come into my life, because I want to fuck shit up for the next 4 years. No, I'm not going to do anything bad. Just
Because of an eco-terrorist.
yeah, like the Monkey Wrench Gang. Anybody ever read that book? Yeah, it's highly great. It's a great book written by this super environmentalist Edward Abbey back in the 70s, and it's do you know?
Does he spike trees in it?
Oh yeah, that's the least they do in it. Yeah.
That is-
But it's a bunch of folks who are a little misguided, but they have this mission to stop the industrial machine from destroying the beautiful world. And they get into some trouble. I'm not going to do that. I'm not going to do that. Whoever, Mr. FBI agent, I'm not going to do that. But I am feeling like super radicalized, like right now.
That's good.
Okay, so it's like that migraine did some shit inside me. It's like twisted some things, and just in a great way. So this is really just a vector with infinitely many slots, and it still has the same. You know, you can take two functions and take a linear combination of them, just like you can vectors, and get a new function out, and that's just a new vector. We can think of it that way. So these Legendre polynomials are orthogonal in the sense that I'm thinking of them as vectors in this infinite dimensional vector space. This is kind of what my thesis work was on, so I'm happy to have a chance to work with this. It was like basically infinite dimensional calculus. Doesn't that sound awesome? I think so. How do you tell? So if I gave you a couple of vectors, let's go back to this guy, and then I gave you another vector that was, let's see, I want this to actually work out. How can I tell if those are orthogonal? Yeah, Josephine.
Can you do like dot product is 0?
Absolutely. Take the inner product, right, or the dot product. Do they ever call it inner product?
I don't know.
That's more of a mathy version of it, but dot product, yeah. So you take the dot product, and the dot product here would actually be what?
0.
0, yeah. So if the dot product is equal to 0, then these are orthogonal. And if you're not sure, what I mean by dot product is 3 times 1 plus 2 times 4 plus negative 1 times 11. And I get 0. So it's a way to tell without having to draw them out, because God, you might have 5 dimensions here and then you're hosed, right? We're kind of hosed even with just 3. It's hard to picture that stuff and know if it's truly orthogonal. So we do the same thing for function spaces. So, but instead of a sum and a product, think about how calculus works. Think about this thing here. This is, right, think about Riemann sums. It's this function sampled, if I have this here, it's the function sampled at some points times some little delta x, and then I sum those all up. Yeah, this Riemann sum relates to this. So we're going to use that idea to think about orthogonal functions. And so what we say is that if I take two functions and get their inner product, their dot product, the infinite dot product, this times this is component-wise multiplication, and this is a sum right here. That times that, add them all up, but there's infinitely many things to add up. If that is equal to 0, that means that F and G are orthogonal. You can't picture it, but you can get at it this way. So what I'm saying here is that any two of these Legendre polynomials, if I take the integral from -1 to 1 of Pn of x times Pm of x dx, that is equal to 0 if those are different Legendre polynomials, no matter what. Pick any two, and you integrate them, and that integral will turn 0. So that's what it means to say you have a collection of functions that are an orthogonal collection. Anybody do that in linear algebra? Do we even do that anymore? No. We used to do it at the end of linear algebra, like function spaces and abstract vectors. But no, okay, I'll shut up. Sounds what?
Sounds familiar.
Sounds familiar. That's good. And that's honestly enough, Daniel. It doesn't have to be more than familiar.
No, I was in one class.
Oh.
Stick very well.
Oh God, was it with the CS department over there, or Anderson or something?
I'm pretty sure it's just some random person.
Sounds like you got a lot out of that course, Daniel.
Yeah, sure.
Don't remember where it was. Don't remember.
I was in Switzerland at the time. So
Oh, were you? Oh, wow.
Yeah.
Cool. It was probably over there. And I'm on tape, so I'm not gonna say any more about that. So that's how we're gonna get the rest. Now, you're not gonna have to produce those by hand. This homework assignment we're gonna talk about in a minute. If you look on page, well, I know I wrote it down in here. In our book, I think it's page 54. Why is it not here? Oh, page 65. Oh, so that was pretty bad. See page 65 for a table of x sub i's in corresponding w sub i's. So they're all computed. There's tables of these things that go on for pages and pages. Or you can ask a computer for them, and they'll give them to you. You are going to need, for the homework, you're going to need the n equals 2 case, which you're already all over. That's the plus or minus 1 over root 3, with weights of 1. But you're also going to need this, the n equals 4 case. So you're going to need the 4 weights, and you're going to need the 4 x sub whatevers. I'm probably going to end up like being the target of a bunch of like right-wing extremists. This video is going to like leak out, become viral.
They're gonna storm ranges.
Yeah. It's happened. It's actually happened to a prof here a few years back. Like,
Really? Do you remember what he said?
There was a student who wanted to do some kind of bake sale that was pretty fucking racist. And so she was like, can we talk about this? And then this person actually went to the media and brought a shitstorm down.
Wow, that's awesome.
Yeah, terrible. Yeah, so it can happen. Isn't that fucked up? Yeah.
That's why I'm not confused.
Maybe
Regis' dark past.
What's this? What?
The Regis' dark past.
It is. It's not even that far past. It was, I can't remember who was president at the time. It was not that long ago.
They'll probably find an article about it somewhere.
So go to there and find that. But I want to show you one last little thing. I want to talk about improper integrals, and I want to show you something really awesome that I saw for the first time in my math life. I was just like working examples, and I was like, what? How could this be? I was so excited. Improper integrals and how to handle. This is with not just the Gauss-Legendre stuff, but any of the quadrature methods. They're all about finite intervals. So they're all about A to B, where A and B are finite numbers. So the plan is to convert an integral, and I'm just going to show you one particular instance, 1 to infinity, or like some constant to infinity. We can just put an A there, f of x dx, to a finite realm here, and we're going to put g of u du, where these are actually the same value. And to do that, we're going to use a transformation. We're going to use a change of coordinates. So let me just do this by example. In general, we can use u equals 1 over x to get that infinity down to 0. Does that make sense? So when x here becomes infinite, u becomes 0. And then the a would just become 1 over a. So notice that this would send x equals a to u equals 1 over a, and it would send x equals infinity to u equals 0. And now we got a nice old integral from 0 to 1 over a, and we can quadrature it with the plans. Any of our favorite plans, trapezoid rule, whatever you want. So let me show you an example of this. Let's see. I spent quite a bit of time on this, and I did some horrible things that I want to share with you. I was just messing around with some changes of coordinate, but I'm not gonna make you suffer through those at all. So let's just take a look at a nice one. Okay, so first, oh God, this is so beautiful. Okay, so let's say I wanted to do this integral here. Let's just look at that, improper integral. Hey, does that converge even? Do we remember, how were you saying, yeah, how come you're...
Right, because it's like, if you have 1 over x to a power and it's greater than 1, then it converges.
That's nice, yeah, beautiful. So these are a class of integrals that you study in Calc 2, and this, if p is bigger than 1, has to be bigger than 1, then this converges. That probably rings some ancient bells, right? From Calc 2, you hear them off in the distance. Cough, a little cough in the forest. So let's do that change of coordinates here, and let me show you how that might work. So first off, I am going to use this substitution. I'm going to write it like this, and that would also imply that x was u inverse. They're reciprocals of each other. This is nice because it's going to help me find the differential change. Yeah, look okay? And then when x equals 1, u equals 1 over 1, that's 1. When x equals infinity, u equals, I hate writing this, but I'm going to do it because it's kind of a bullshitty thing to write, but let's do it anyway. 1 over, everybody thinks this. This is something we all think anyway, right? I mean, we're trained to not say this or write this, even though people do it all the time. Does this all seem reasonable? Is that a question, Dan? No.
No, I'm just curious.
Okay, cool. Let me rest for a second. I know I'm on a rampage. Just to be clear, when I say I want to burn shit down, what I mean is I want to work at a grassroots level to facilitate change that I want to see in the world. Just to be clear.
Straight to the monarchy, the oligarchy.
Exactly, yeah.
It's right there, get rid of all their supplies.
Exactly. Cool. So, could you go ahead and rewrite that? Because I want you to have the fun, the glorious moment that you'll see. Do that change of variables and look in amazement. This is just one of the things I've never seen before. It's not the one I was talking about before. It's kind of crazy. Been writing a lot, Lavina? Oh, you're not shaking your hand out, it's the pen. The pen's garbage. Got it. Somebody like give a barbaric yop when they see this. Yeah. Yop understood. But it is kind of cool, isn't it? I was shocked, honestly. It is pretty cool. It is. It's like, what? What?
Just don't know if I did the right thing.
We'll see what you get.
I don't even know.
Yeah. Well, you didn't change the limits. That's the only problem. So the 1 goes to a 1, but then the infinity goes to a 0. There you go. Yeah, you did the actual integram part perfectly.
Just a baffling answer.
This is just direct plug in. Don't forget to change the limits. 1 stays at 1. You're basically taking the real line and you're pivoting it around 1. So you're taking 0 and moving it to infinity, keeping this point fixed, and you're taking infinity and moving it here. So you're like going and doing the stretching and all this stuff that's required. Notice that this is u to the negative second, so is this. They cancel. I am left with negative integral 1 to 0, integrand of 1 du. I don't like the limits being like this, and so if I flip the limits, what do I do to the integral? If I change the position of 1 and 0, what do I do to the integral? Make it negative, and I already got that nice negative out front, so it becomes positive. Integral 0 to 1 du. 1. Yeah, yes, it is concerning. All right, so that's cool fact 1 that I wanted to show you. And you will be doing this on the final. You're not doing this on this homework assignment I just put up. What's that?
What is the final?
It's going to be a take home, so it doesn't matter. Yeah. Does that sound okay?
Yep.
Awesome.
Okay, yeah, good. We're gonna be all right. So this one I was looking at, I thought, well, this is one of my favorites because it's arctangent, and I just love arctangent. But let's talk about how I would do this. Now, what happens if I try to just look at this and do this swap? What happens? Does it move me forward? Why not? And Brendan, you were saying no? Okay. No, that's a double no. Okay.
Just because you've got like 1 over 1 plus x squared, so you can't just substitute in your 1 over x for u. So there's not like a good way to substitute it
Well,
and get it to like.
let me actually come back at you with that. I could do that, right? And then I could rewrite the integrand.
But then you still got like, you still got the 1 plus like that goofy shit. It's just gonna be weird.
Let's see. Okay, we're gonna see here. We're gonna see. So if I do that, then I've got just the integrand part, right?
Mm-hmm.
We'll look at the different. Oh, I guess the differential is right. We already computed. What am I doing? What am I doing? That's what I'm doing. So this integrand would become 1 plus, and then this is 1 over u quantity squared, right? I'm going to leave the limits alone, and then the dx becomes negative u to the negative second du, and so I could work that out. I think it turns into the same function.
It's because you're starting at 0. Right?
That's the one I was thinking about. So,
I totally missed that. I just didn't even.
it's okay. It's all good. It's all good. We'll take a look at this in a minute because I think we're going to want to. But notice that if where will 0 go? Infinity, and infinity goes 0. So it just flips them. It doesn't really get me anywhere. And remember, it's this move. I'm pivoting around the line x equals 1. So it doesn't really change things a whole lot. So the way to actually navigate this is to break it into 2 integrals. I'm going to break it into a definite integral and an improper integral. So the first part is going to be really just lovely. We could quadrature our way to joy with that, any of the methods we've used. So trapezoidal, Gaussian, whatever. That's easy. And plus this one. Now this one I can do a transformation on and get something meaningfully different out. So let's do that part together. Did you all see what I'm saying here? That this integral here, if you think of this, and if that's not obvious what I just wrote, I think it might not be. This curve, y equals 1 over 1 plus x squared, looks like this. Looks like a bell curve. And what this is asking for is this area from 0 to infinity. So what I've said over there is let's break it into 2 integrals, this nice finite one, and then this crazier one over here. Does that make sense, thinking about the areas? So that's the way I like to think about all these things. I have a picture that works best for me. So let's do the transformation on this piece. And let's use this transformation that we've got here. So we're gonna transform. The coolness is about to happen. And we'll do this together. We'll kind of like go through and hold hands, make a circle. It's gonna be great. Transform, we're gonna let u equal 1 over x. In other words, x is u to the negative first. And this is literal, I'm just rewriting what's over there. And then we come in here and we do that with that kit there. The 1 goes to 1, the infinity goes to 0, as we've seen. And then this integrand goes to 1 over 1 plus 1 over u squared, right? Because that x is 1 over u. So I'm just going to write it like that. And then notice that du is negative 1 over u squared du. So this is 1 over u squared du. Negative, and there's a negative. I'll put it up front. Take a moment, simplify. Tell me what you see. This is the part I was like, how did I live this long and not see this? Oh yeah, I appreciate you. Yes. Isn't that crazy?
That's wild.
It is wild. What a wild ride. You see it?
That's pretty cool.
That is freaking amazing. What? Arctangent is a hell of a thing.
Yeah.
Are we all seeing that? We're seeing.
I'm seeing something weird and I guess this week.
That sounds good. Weird's always exciting.
That doesn't make sense.
So your limits here, so that should
Yeah.
keep the integral separate. So put a little.
So I
bec-
should just do 0 to 1.
Yeah, because you're gonna have to flip the sign, so
Yeah.
that would become a plus. You see what I mean?
Oh, and I did that. At first
Yes.
I like, that's even weird.
Yes, yeah. They don't cancel out, which that would be. That I don't know. I would probably just go home if that happened. But this integral is this integral. They are the same. So this area here is exactly that area there. Madness. But that means this whole integral could just be rewritten as 2 of these. And we're good to go. Quadrature. Dang, yeah, that was a great moment. Just chilling in the basement with our adopted bunny friend. He was really being irritating, just like always wants to throw my tea over. Just anytime I have it, I was like, you little fucker. He comes in and he grabs the lid with his teeth or the rim and just pulls it over every time. He knows where it's at and I keep moving it. I like sitting there, keep moving it, and he keeps like going around. So he's really quite a miscreant. All right. Happy if that's not looking good to you, if you like need a little help seeing this, happy to help you. But let's take a look. Could you please open up World Class? Because that's where your assignment will be. It's in the actual assignment that I created. In a way, I'd kind of prefer hard copies, stapled hard copies.
It's not in the assignment.
What? Seriously? I know you're not lying to me.
like the assignment's up, it's just not like attached. There's no like.
I think I got that.
Here's
Oh.
the work for you.
Okay. You found it?
No.
Oh God. Okay.
And you click on like the assignment and it does not have the questions. It's just like
Okay.
please submit a document.
All right. I'll fix it right now. I'm just gonna email it to you all. Just give me a second. I think I got that. What? From you, Lou.
Huh?
You say that a lot, and I think I
Oh.
like it. Just that the cadence of it all. What? Not that you're the first person to ever say what, but. Alright, I gotta go to freaking Dropbox. So this should be interesting. Oh, cool, I can log in with Zoom. Okay. One thing you can check out, check it, go to, and so this, I forgot I did this, there's code. There's actually Gauss-Legendre code in the Quadrature section of the content. So if you wouldn't mind checking that out, you'll have to cut and paste it into Jupyter while I get this stuff going. But check it out, it's pretty sweet, and you can maybe even use it to answer part of the homework. What am I doing? Googled. And it should work pretty good. Sometimes there's problems if you use the web Python. That sometimes doesn't like the way I do those inputs. But if you're running it on an installed Jupyter, it should just prompt you for all the particulars you're interested in. I think you'll have to hard code the function. That's about it. Okay. Oh, here it is. Is the code running?
Yes.
Yeah.
Cool. Oh, fantastic. So just give it a little play around, because you can pick a lot of nodes there, and maybe just look at it to see that sweet routine that we're calling from NumPy that actually does compute those coefficients and nodes. Why can't I see the date? Shit, I'm just gonna go make copies of this. I think I can do that. I'll be right back.
Shoot, should have been like maybe we shouldn't have homework. I know.
I hope it times out. You know what's that? Do they? Cool, thank you. I appreciate the peace of mind.
Thank you.
You're so welcome. This is a handwritten one. Oh, sorry. What'd you say? Yeah. So you did say what the fuck, right? So yeah, you can go.
Are you talking to me?
No.
Oh.
Mr. Daniel here.
That's a good age.
No, my senses haven't gone that much. This will be your last assignment, and then the next one will just be the take-home final. That's sad? Oh, then it won't be. I think you definitely get more.
Laughing, he said that's sad.
What?
She said this on last assignment.
I think we could have gone without this. We should have just done it. I agree. Yeah. You know, honestly, like, maybe.
So real.
Yeah.
Spoken from the heart.
Maybe this should just be the
Like, you know, just give us the
just a
final
whole
before
month for
Thanksgiving.
a
like-
final.
Yeah, do it over Thanksgiving. How about that?
Yeah.
Just for you though. Everyone else let's do the week after.
No, like we get it before Thanksgiving.
Like just a whole month just to do this final. 'Cause I don't like three more questions.
You're sick of my brutality and my unfairness and my inflexibility. I don't
Really,
like
New York. We're radicalizing.
Honestly,
against
you
it.
just
You're
give us
radicalizing, yeah.
so much work. Too much.
All right, let's look at this. No, we're gonna fucking do this. It's really not that bad, but you'll have to pull together ideas. You'll have to like kind of know what just happened the last 2 or 3 weeks. That's all I'm asking.
Might be too much.
So, please do not use less than 4 decimal places of precision. Right? This is not a class for hundredths. We're not a hundredth kind of class. We're a 10,000th at a minimum kind of precision level class. So, use 4 decimal places, and you will find that the table of values actually gives you 4 decimal places, so you can't really do more than that. So let's look at what I'm asking you to do here. The first problem, use the recursive trapezoidal rule to evaluate that wicked integral. Now, that is not equal to natural log of 1 plus natural log of tangent x. If anybody does that, I'm gonna blow a gasket. Natural log is not a linear function, so it's gotta stay that way. What I want you to do is show the computations for the first 3 iterates. Now what I mean is, you're gonna find I naught, and that's your initialization. So this is the, yes. I naught is literally, oh sorry, it's not that, it's 1 trapezoid is what I mean by before. So it's just a single trapezoid. You'll have to compute that. That's the value of the function at the endpoints averaged, you know, over the interval. It's not craziness. And then use the recursive trapezoid rule to find the rest, right? Remember how that goes. There's you start having the h and all that stuff. So you'll want to ask questions on this, no doubt, but you're going to need to get in and know what your questions are first. I'm happy to talk about them. Number 2, use the 4 approximations from part 1 and perform a Romberg integration. So what you will have, let me show you what this will look like. Find this guy. What you're going to get in part 1 is a list of values that look like this. You're going to have I naught, I1, I2, and I3. This is what I mean by first 3 iterates. So this is 8 panels. This is 4 panels, 2 panels, 1 panel. Trapezoidal stuff. But use the recursive one. Don't go do each of these by hand. That's way too much work, and I want you to know the recursive version. And then Romberg this, right? So we're going to use the fact that this first iteration is order h squared.
The next one will be order h to the 4th. So here you'll have 3 things, here you'll have 2 things, and you'll do one more, and you'll get an order h to the 8th final version. This is going to be a triangular table. Goes up like that. It's going to look like the Richardson stuff. It is the Richardson stuff for a very special case. So this is the answer I'm looking for. Please provide me that table. Please show me that table. Don't just give me that. Don't just give me an Excel sheet and say, see Excel sheet. Please write one document. One document for this, okay? Right? That's our new law. One document for all. What brings us all together. All right, number 3. This is actually kind of cool. We haven't done anything like this. This is how a scientist would actually use this type of quadrature. You have a data set. You have a sampling from some thing that's happening. This could potentially be a thing that's rotating through space. And the x-coordinate is simply the radial sweep of this thing. And maybe you could think of f of x as like the velocity of this thing, or I don't know, whatever. It's a sampling at 5 different points of some event, something that's happening. Use the trapezoidal rule 3 times. First one for the whole full width, so that's just a single trapezoid. Then do 2 panels where you'll use the outer, the middle, and the ends, so the outer and the middle. And then 1 more trapezoidal rule where you have 4 panels, taking them consecutively, 2 at a time. Create those values. So again, you're going to have a thing here. It's actually going to be fewer things. It's going to be a Romberg table, but there's only 3 initial things to work with. And then Romberg that sucker up to an h to the, probably, let's see, so these, yeah, so you'll get something here, here, and then your final one will be an h to the 4th estimate on that one. And then on the back, there is something on the back. So this one we're going to get to practice Gauss-Legendre integration. That is one hell of an integrand. And this can't be done without numerical methods. So when you start looking at this, I hope you're realizing this is actually not that hard. This 4th problem is do it with 2 integration points. Plug plus or minus 1 over root 3 into the integrand. Add. Done. Right? Well, you will have to convert them. So keep in mind that you will have to do one thing, that the plus or minus 1 over root 3 is for this interval, so you're going to have to do the conversion to the appropriate interval. So here you're going to have to do that change of coordinates that we talked about, the linear change. Then go to the table I referred you to in the book on page 65 and do it with 4 nodes. Not much more work, a little bit more. And then on 4, go find your favorite tool that you're not cheating, you're using a numerical tool. Go find something that will give you a precise answer. You can use Wolfram Alpha, Symbolab. Anybody got any others? Where do we go when we need an integral? I don't know.
I just go to integralcalculator.com.
Oh, I like that.
I like that one.
Okay, integralcalculator.com, thank you, good reference. So go there, get a precise one, compute the relative error, not the absolute error, the relative error. All right, let's call it a day. Thank you, friends.
Wait, was there a due date to the...
Yes, thank you. Let's say next Friday. Does that sound good? I kind of don't want to push it past that. I really want to stick to next Friday. So try to help me.
Monday of Thanksgiving week.
Yeah, I don't know what's going to happen that Monday. So, yeah, we're going to go for the Friday before Thanksgiving, Brendan, but I appreciate the suggestion.
Hear me out. After Thanksgiving. Hear me out. Thanksgiving Day.
Hear me out, never.
What?
Okay.
Now you're talking.
Head first.
Before grades are due.
Alright, you said it, not Not me.
I know. I'm just full of ideas.
Radical.
Burning that shit. Turning my key. Oh my god, am I still on? Josephine!